Welcome to Boson Buzz, where we dive into the coolest scientific ideas and breakthroughs shaping tomorrow's world. Look around at the modern world and you will see a landscape defined by concrete. It is the literal foundation of our cities, our bridges, and our infrastructure, the most consumed substance on Earth after water. Yet, from the moment this artificial stone is poured, it begins a silent, slow-motion battle against the elements. This is a war of attrition that we have been losing for centuries. Weather, pressure, and the relentless force of time conspire to attack our structures, creating tiny fissures and cracks that steadily grow larger with each passing year. Our only response has been a cycle of constant, costly, and disruptive repair that plagues every municipality on the planet. Crews are dispatched, roads are closed, and massive sums are spent just to maintain the status quo, to patch over the symptoms of decay without addressing the root cause. It is a trillion-dollar global effort that feels as ancient as construction itself, a tax we pay for living in a built environment. But what if we could fundamentally change the very nature of this battle? What if, instead of endlessly patching our buildings from the outside like a clumsy bandage, we could give them the innate ability to repair themselves from within, just as a living organism heals a cut? This is not a science fiction fantasy. It is the revolutionary promise of a new frontier in material science, one that seeks to transform our static, decaying structures into dynamic, responsive, and truly living systems that can defend themselves against the passage of time. To understand this revolution, we must first look at concrete's greatest weakness, a paradox of its own nature. For all its immense strength and compression, able to support skyscrapers and massive bridges, it is incredibly brittle and prone to cracking under tension. These aren't just the large, visible faults you might see on an old sidewalk. From the very day it hardens, concrete is secretly laced with a vast, intricate network of microscopic cracks, invisible to the naked eye but present nonetheless, an inevitable result of the chemical process of curing and drying. These tiny flaws are the material's hidden Achilles heel, its fatal vulnerability. They act as secret pathways, allowing water and air to seep deep into the heart of the structure. This infiltration is where the real, insidious danger begins, because virtually all modern concrete is reinforced with a skeleton of steel rebar, which provides the tensile strength the concrete itself lacks. When moisture and oxygen reach this embedded steel, a predictable and destructive process begins: rust. The chemistry of corrosion is relentless. As the steel rusts, it expands to a much larger volume, exerting tremendous outward force from within the concrete's core. This internal pressure inevitably cracks the surrounding concrete further, leading to a destructive cycle known as spalling, where entire chunks of the material break away and eventually to catastrophic structural failure. What began as a microscopic, invisible flaw, no wider than a human hair, can escalate over years into a critical threat that compromises the safety of an entire structure, revealing the fragile nature of our seemingly solid world. For decades, the only solution was to fight force with force, trying to make concrete denser and stronger. But a group of innovative scientists in the Netherlands proposed a radical new strategy. Instead of fighting nature, why not recruit it? Their inspiration came from the resilient world of microbes. They chose a specific family of bacteria, known as bacillus, renowned for their incredible toughness. When conditions become harsh, these bacteria can enter a state of suspended animation, forming a nearly indestructible shell called a spore. In this dormant state, they can survive for decades without food or water, waiting patiently for the right conditions to return. This biological superpower became the key to a self-healing system, turning a simple microbe into a microscopic maintenance worker embedded within the stone. The challenge was delivering these bacterial repair agents without weakening the concrete. The solution was an engineering marvel in miniaturization. Scientists developed a method to mix the dormant bacterial spores, along with a special food source like calcium lactate, directly into the concrete mix. These components are packaged inside tiny, biodegradable capsules that protect them during the concrete's initial harsh setting process. As the concrete hardens, millions of these microscopic repair kits become permanently embedded throughout the material. They are dormant, silent, and completely invisible. For years, nothing happens. The concrete appears utterly normal. but this system is designed for the long term, a hidden insurance policy waiting for the moment it is needed. The true magic of this system begins only when the concrete is actually damaged. The moment a crack forms, no matter how microscopically small, it creates an opening in the material's defense. Water, the universal solvent and the primary agent of decay, inevitably seeps into these newly created fissures. This intruding water is not just a threat, it is the specific trigger designed to activate the repair process. It dissolves the protective capsules surrounding the dormant bacteria, effectively waking them from their decades-long slumber and simultaneously releasing their stored food supply into the immediate environment. Suddenly active after years of waiting, the bacteria spring to life, beginning to feed and multiply rapidly in their newly hydrated environment. As they metabolize the food, they initiate a natural biological process that produces a very specific and incredibly useful waste product: limestone, which is, not coincidentally, the primary chemical component of concrete itself. In essence, these trillions of microscopic microorganisms are acting as a distributed, automated factory, excreting tiny, perfect bricks directly on the construction site of the crack. This limestone precipitates out of the solution as robust calcite crystals, which gradually grow and multiply, interlocking with each other and chemically fusing with the rough walls of the concrete, seamlessly filling the crack from the inside out over a period of several days or weeks. It is a silent, slow, but remarkably effective process of biological masonry, restoring strength and integrity without a single human intervention. The ability to autonomously heal cracks is a monumental achievement, but it is truly just the beginning, the first step into a bold new field known as engineered living materials. This philosophy pushes us to imagine a future where our infrastructure is not inert and passive, but biologically interactive and responsive to its environment. Concrete surfaces and walls, for instance, could be engineered to contain specialized bacteria that act as tiny, constant air filters, absorbing pollutant particles from smog and breaking them down into harmless substances, actively cleaning the air in our densest urban centers. We could develop building materials that regulate their own temperature by adjusting their porosity in response to heat, or that can absorb and dampen the relentless noise of traffic, creating pockets of quiet in a chaotic world. We could even pioneer the use of sidewalks and curbs that glow with a soft, natural, and safe biological light at night, using harmless light-producing bacteria to illuminate our paths and increase safety, all while reducing our reliance on electrical grids. This represents a fundamental and profound shift in our relationship with the built environment. We are moving from an era of static construction, where we assemble dead materials, to one of dynamic cultivation, where we grow and program living systems. Our buildings and bridges of the future may not just be built, but grown to intelligently interact with and adapt to their surroundings, creating a sustainable, resilient, and truly symbiotic relationship between nature and the human-made world. Of course, this bright future of living infrastructure is not without its significant and practical hurdles. Currently, producing this specialized bioconcrete is more expensive than traditional methods, a critical economic barrier that must be overcome for widespread adoption in large-scale public projects. There are also profound and unanswered questions about the long-term viability of the embedded bacterial ecosystems. Can these microscopic laborers truly remain dormant, viable, and effective for the decades or even centuries we expect our major infrastructure to last? How do they perform in the vastly different and often brutal climates found across the globe, from freezing Arctic tundras to scorching deserts with their extreme temperature swings? Furthermore, introducing biological agents into a material traditionally considered inert requires new standards, new testing protocols, and a shift in mindset for the entire construction industry. Despite these formidable challenges, the global research community is making rapid and encouraging progress, driven by the immense potential payoff. If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool, futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.